Welcome. In the last class, we have seen how different compartment models can be used, combination of well-mixed reactor, plug flow reactor, bypass, dead zone, how all these combinations we can fit to experimental data that tells us something about how the actual equipment, how the actual reactor is performing, and then we can analyze and understand and improve how the performance of the equipment. Let's just go forward in the syllabus and just to get you started once again, this is where we are in our syllabus. We are on the third part of our syllabus. We had seen all these RTD, estimation of dispersion, backmixing, dispersed plug flow model, tanks in series model, compartment models, all these we have seen. Now we are going to look at some of the design aspects, how we can use this information to calculate, if it's a reactor, how we can calculate conversion. Just to help you revise some of the things that from the previous lecture, what procedure would you adopt to predict the E curve for a combination of well mixed and plug flow reactors with dead zone bypass? What considerations should you take into account while fitting the model parameters to experimentally observed RTD data? What features in the RTD data listed below indicate about the performance of the equipment? Suppose in the RTD experiment, RTD data of an actual reactor or actual equipment, you see a long tail. What does it tell you? You see that actual residence time is less than the theoretical residence time. What does this tell you? You see multiple peaks, you see early peaks. What does all these tell you? It tells you something about how the equipment is behaving. Is it possible that a multiple combination of compartment models will fit a given RTD data? And if yes, how do we decide which combination is better, which combination works well, which combination is able to characterize our experimentally observed or our actual RTD? Okay, so this is where we are. We had said that we could use the concentration equation and we could predict performance using, let's say, computational fluid dynamics. That's not what we are going to do. This is what people do nowadays, but we are not doing that just now for the purpose of this course. We would rather experimentally measure and fit combinations. We have fitted well mixed tanks in series, we have fitted dispersed plug flow model, we have fitted compartment models. Now is the time to use all this fitting and characterize or calculate conversion. Okay, so what is the meaning that suppose there is a tank here and there is an entry, liquid is coming in. Let's imagine that this liquid consists of many tiny particles, many packets of fluids. Let's call this as a macro fluid or a segregated fluid. Each packet is going to spend some time and go out. Let's say there is one packet here. Let me just put some colors if you like. Let's say there is a packet here. This packet spends 3 minutes and goes out. Another packet spends 5 minutes and goes out. Another packet spends 12 minutes and goes out. Another packet spends 1 minute and goes out. All right. We can calculate conversion in each packet and what would be the overall conversion as a combination of all of these packets put together. That's the advantage of E-curve. So if you think of one packet of fluid, outlet conversion for that packet would be just based on what would be the, as if that packet is not mixing, it would just be based on how much time that packet is spending. And then overall combination of all such packets put together would be our overall conversion. So we can write outlet concentration or conversion, Ca outlet divided by Ca inlet would be integral 0 to infinity Ca for that particular packet at the outlet divided by Ca at the inlet for that particular packet. This is for one packet. How much time this packet is spending? E curve, ET dt is the fraction of time spent by this particular packet, and add up all such packets, then we will get the overall conversion. Or you can subtract 1 from both sides, and remember that ET dt 1 is just 1, so it allows me to take 1 inside, right? And then this is XA would be integral 0 to infinity XA for the packet into ET dt. Let's start using all these things. Okay, so if it's a first order reaction, if a packet spends time t in the reactor, what is an expression for Ca by Ca inlet and XA for that particular packet? Each packet is behaving like a batch reactor because it is not mixing with other. It is spending a time 3 minutes, 1 minute, 4 minutes, 5 minutes, whatever. As if there is a combination, each packet is behaving like a batch reactor and it is spending a time t for a batch. Okay. So then Ca by Ca inlet for the packet would be e raised to minus kT. XA for the packet would be 1 minus e raised to minus kT. This is like your batch reactor performance equation. Okay. Do you agree? What would be the overall conversion? 1 minus e raised to minus kT Et dt. And if you integrate, you will find it is k tau divided by 1 plus k tau. This is now our performance equation for a well mixed reactor. See, the performance equation which we had got in our undergraduate course, we can get the same from our RTD data. And if the fluid is a macro fluid, not mixing as if there are packets of fluid inside that main fluid. Let's go forward. So let's say there is a first order reaction being carried out in a reactor. This is our reactor. This has given this E curve. This is our actual RTD data. The rate constant is 0.1 minute inverse. Calculate the conversion using this data. Remember, ET curve shows tau equal to 13.91. Sigma square is 36.85 minute square. Okay. Solve this for yourself. Use these formulae. Pause. Okay, so if reactor shows an ideal plug flow behavior, what would have been the conversion? XA would have been 1 minus e raised to minus k and tau. It would be 0.7512, 75.12%, 75.12%. Okay. If reactor showed well mixed behavior, XA would be k tau divided by 1 plus k tau. We would have got, so this would be 0.1 multiplied by 13.91 divided by 1 plus 0.1 into 13.9. We would have got XA is 0.5818, that is 58.18%. Okay, this is XA subscript. Now, but this reactor is not behaving like a well mixed behavior. It is not behaving like a plug flow. Its behavior is like this RTD E curve. C out versus time. This is going to give us our E curve. We have already got this. We have already got this. We have already done this problem. We have already got the E curve for this particular reactor. Now, what would be the conversion? Calculate. Use these formula. Okay. Here's the solution. So this is our T versus ET. This is our T versus ET. This is our actual experiment. What would be Ca by Cai? It would be e raised to minus kT. Means a packet which is spending 4 minutes in the reactor. Packet which is spending 4 minutes in the reactor. Ca by Ca outlet would be e raised to minus k. K is 0.1 into 4. Packet which is or group of fluid packets which are spending 6 minutes, it would be e raised to minus 0.1 multiplied by 6. This would be e raised to minus 0.1 multiplied by 9. This would be e raised to minus 0.1 multiplied by 11. This would be e raised to minus 0.1 multiplied by 15, and so on and so forth. So this column tells you what is the CA in that packet which is spending 4 minutes, CA in that packet which is spending 6 minutes, CA in the packet which is spending 9 minutes. Now all I have to do is take an average with respect to this ET. So I will calculate CA by CAI multiplied by ET. It is 0.673 multiplied by 0.0079. This is the outlet concentration, but this much fraction of the total is having this much concentration at the outlet. See, 0.0079 multiplied by 0.6703 is 0.0053. 0.0394 multiplied by 0.5488, you will get 0.0216. 0.0630 multiplied by 0.4066, you will get 0.0256. 0.0788 multiplied by 0.3329, you will get 0.0262, and so on. This is CA ET dt. Now we have to just integrate this from 0 to infinity, 0 to infinity, or 0 to 35, because there is nothing beyond 35. Concentration has already come to 0, E curve has already come to 0. Okay. So now use the trapezoidal rule. Use the trapezoidal rule. Trapezoidal rule between these two, you will get this. Trapezoidal between these two, you will get this. Trapezoid between these two, you will get this. And integration means add up all such trapezoids. You will get CA by CA inlet is 0.2915, which means conversion is 1 minus 0.2915, 0.7058. This is 70.85%. So our real reactor will give you 70.85% conversion. If it had behaved like plug flow, it would have given 75.12. If it had behaved like well mixed, it would have given 58.18. So our real reactor is actually behaving in between a well mixed and plug flow behavior. There is a scope to make it plug flow, you will get 75%. As such, as it is operated, it is behaving, it is giving only 70.85% conversion. That's how the RTD data is useful in actually predicting the conversion that you will get in the reactor. Let's go forward. Okay, just to summarize, if we use well mixed tanks in series, when we had 5 well mixed tanks in series, each one was tau I equal to 2.73. What would be the conversion? Solve it for yourself. Pause. Conversion would be CA out at the end of 5th reactor divided by CA in the first reactor would be 1 by 1 plus k tau raised to 5. Well mixed tanks in series for conversion, you have done it long ago in your undergraduate course. So it will be 1 divided by 0.1 to 0.73 raised to 5. So it's almost 0.3. XA would be 70%. Conversion would be 70%, 0.7, 70%. You see, it's very close to this value, because 5 tanks in series is approximating our actual reactor behavior. RMS is very less, root mean square error is very less. If we take 6 well mixed tanks in series, you will get 0.7084, 70.84. So you see, there's not much difference between them. If we had used plug flow followed by well mixed, what was the fitted values of plug flow, tau plug flow and tau well mixed? Go back to previous lecture, use these values, use these fitted values and calculate what would be the conversion. Do it for yourself. Same way for well mixed followed by plug flow. Do it for yourself. Pause. We had found that tau p is 7.55 followed by well mixed, tau well mix. This is not tau plug flow. Let me just change. This is not tau p. It is tau well mixed. tau well mixed 11.06. What would be the conversion? What would be the conversion? Do it for yourself. Pause. For a plug flow, it would have been 1 e raised to minus k tau p. For a well mixed followed by plug flow, it would have been 1 plus k tau well mixed. So Ca out by Ca in for the well mixed outlet of the well mixed divided by inlet to the plug flow, it would be e raised to minus k tau p divided by 1 plus k tau wm. Calculate, you will get Xa equal to 77.68. 77.68% we would have got conversion. Well mixed followed by plug flow, you would get the same expression, right? So plug flow followed by well mixed or well mixed followed by plug flow will have the same conversion because it's a first order reaction. Had it been a second order reaction, things would have been different. Plug flow followed by well mixed or well mixed followed by plug flow is not the same. You see, now different combinations I can use and I can predict what would be the conversion. And that's the use of RTD. Let's go to further dispersed plug flow model. What we'll have to do is Vz del Ca by del Z is dt del square Ca by del Z square Kca. If we write in terms of conversion, del V del Xa by del Z, turbulent diffusivity, turbulent dispersion, del square Xa by del Z square K 1 minus Xa. If I make it dimensionless using Z bar as Z by L, and we can calculate now, we can simplify. This is the expression that we will get. Peckley number, our Peckley number was something like 8, 9. See the lecture, that lecture, and this is the value. So if I have to calculate conversion, I will have to solve this partial differential equation numerically, and then we will be able to calculate what is the conversion. Okay. Fortunately, these things have been done and they have been put in the form of a chart for us to use. So these two authors, Werner and Wilhelm, gave an analytical solution for this equation, for a first order reaction, and this is how their analytical solution looks like. Okay, we don't have to really solve using this, we can use this chart. This chart tells us what is the volume divided by the plug flow volume for different values of 1 minus Xa. These lines are for different values of dispersion number or 1 by Peckley number. This line is for dispersion number of infinity, Peckley number of 0, 1 by infinity. This line is for a Peckley number of 1 by 16. This line is for a Peckley number of 1 by 4. This line is for Peckley number of 1. This line is for a Peckley number of 1 by 0.254. This line is for a Peckley number of 1 by 0.026, 16. This horizontal line means is for a Peckley number of infinity, means plug flow. So it is V by Vp is 1. See? Okay. So we can use this expression or we can use this chart, whichever one we like. And since we already have an analytical expression, let's use this. So Ca by Ca naught is 1 minus Xa. We can use this expression. A is this 4k tau divided by d by L. So for the RTD, we had got this Peckley number 8.34 as the best fit. So if I use these values, k is 0.1 minute inverse, tau is 13.91. A, if you calculate from here, A will be 1.29, and then Xa if you calculate, and then Xa 1 minus Xa using this expression, and Xa you can calculate. So this shows that we will get 70.79% conversion. So RTD helps us to calculate conversion for a first order reaction. For not a first order reaction, we can use these charts. So this chart is for first order, but similar charts you can make, or you can solve this numerically for yourself. Don't need to rely on any chart and calculate conversion. So that's how RTD is helping us to calculate conversion. And we can compare now with our actual reactor. Actual reactor in the plant, maybe having maybe 65% conversion, or maybe having 75% conversion. We have fitted different models now, and we can calculate for different models what kind of conversion we will get. This is the advantage of RTD curve, or this is the advantage of measuring the residence time distribution. So we will stop here with respect to RTD part of this course. Just some homework for you. We have done, if you think about Fogler's book, 4th edition, we have done chapters 13, 14. You can solve this problem: 13.5, 13.7, 13.10, 14.3, 14.4, 14.7, 14.21. All these problems you can solve. 11 spill, we have done chapters 11 to 16. You can solve problem 12, 11, 13, 11, 14, 11, 15.3, 15.4, 15.5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 problems I am assigning. Solve these 13 problems for homework. They are based on our lectures, all these 5 lectures in the in lecture 6, 7, 8, 9, 10. Okay. Solve these problems. Unless you solve these problems, all these concepts will not be clear to you. All these concepts will not be clear. So you have to solve problems so that you are able to understand, digest, comprehend this information. Once you have done that, then only go to the next lecture, then only go to the next part of the course. Okay. So good luck in solving all these problems, and I will see you in the next lecture, next part of the course.